All right, well, we had some, I just gave some homework back, and we do have some homework due for today. They were these word problems, similar to this translation that we finished up with last time. And we did a couple of them on the board for you. I think 9.29 is the one that was, we did a few of those last time. Actually, before I ask if there's any specific questions, I was going to do the first part A of 9.34 and 9.35 as well. Maybe I'll just go ahead and do that. And then see if you have any questions. So let's take a look at 9.34. Does anybody have a book there? So this is 9.34a. Okay. And we're going to define, I think I gave in the web page, I said define loves xy as person x loves person y. So define loves xy as person x loves person y. And so oh, actually, I shouldn't put a parentheses around this because this is not a theorem, this is an exercise. Are you with me? So that's how we distinguish here. Okay, so 9.34a, can somebody read that? What is 9.34a? It says what?
It says everybody loves somebody.
Everybody loves somebody. Hoo-hoo. Oh, that's nice. That means that we all have some love in our hearts, right? There is nobody who doesn't like anybody. Oh, that was generalized. That was generalized to Morgan.
There might be some people who aren't liked by everyone else. Who aren't liked.
Actually, that's a good point. There might be somebody who is not loved by someone, but at least everybody, at least we all have some love in our hearts.
Feels loved but not loved.
Okay, yeah. Okay, so what was it? Everybody loves somebody. Is that what it was?
Can you love yourself?
Everybody. Oh, loves XX. It would have to be symmetric. Or no, reflect. No, not symmetric. Reflexive, right? Anyway, because remember the reflexive property of equals? Mm-hmm. It's x equals x. So if instead of being equals, if it was loves, it would be loves XX. Yeah. So if everybody loved himself, it would be loves would be reflexive. Okay. Anyway, it's everybody loves somebody. Okay, so how would you do this? Everybody. Everybody. So is this a for all, or is it there exists?
For all.
This is for all, because it's everybody, right? It's for all x, and we'll just annotate it with type. Let's just say that P is a person, okay? So for all x, type P, range true.
Loves xy.
But what's y? Y would be a free variable if you said loves what? If you just said loves it. Ah, it's a there exists. So for every single person here, there exists a pot. Yeah. So
everybody has a y.
Yes, everybody has a y. So there exists a y type person, range true, such that what? Love, yeah, such that loves xy. And then the rest of them are similar, right? How about 9.35? I think we said here, let's let t be a natural number. Or let time t. T is going to be the time, because this is something about all the time, you know, let time t be a natural number. Okay. So what we have is t is of type n. Okay, so time 0, time 1, time 2, time 3, time 4. Time 0 is the starting, that's the big bang, that's the start, you know, starting of the time. And let's let fool PT, fool PT means what? What does this mean? Means you can do what? Fool person P.
Person P fools person T.
No. T is going to be time on this one. Okay. Means that you can fool person P at time T. Are you with me? So fool PT means you can fool person P at time T, right? Now, you know, I don't, you know, I keep hearing, have you heard the expression, well, you can fool some of the people all of the time, or you can fool all of the people some of the time, but you can't fool all the people all the time. Have you ever heard of that expression?
Unless you're Hitler.
Well, I think even Hitler couldn't fool all of it.
All the time.
Yeah, you know, I don't know where that phrase came from. I mean, have you ever heard that phrase? Well, you can fool some of the people all the time, or you can fool all the people some of the time, but you can't fool all the people all the time. Have you not heard that?
Yeah.
I've heard it. I don't know where.
Yeah, but anyway, it's okay. So now in A, what is it? So what is A? What does it say? What is it asking us to write down in part A of this?
You can fool some of the people some of the time.
You can fool some of the people some of the time. You can fool some of the people some of the time.
There exists a person that can be fooled at some time.
Yes,
There
exists a person. Yeah, very good. Okay, so there exists a P. There exists a person, P-type person. You know, capital P is a person, say. Okay. Range true.
There exists a time type M.
Such that, and now we have an exists inside of an exists, because there exists a person who you can fool at a time, right? At a particular time. So there exists a what? A time type natural number, range true, such that what?
Fools.
Fool PT. Fool PT. Now, tell me again. I know you know this, because I've asked you a bazillion times before. What's the definition of a predicate?
Function.
It's a
Return
function
Boolean.
that returns type Boolean. By Jove, I think we've got it. Now let me ask you this. What is this loves XY? It is a what? It's a function, loves, has two variables. And each one of these variables, is each one of these variables a type Boolean?
No.
No. But on the other hand, loves does do what?
True or false?
Returns type Boolean. So therefore, loves is a what?
Predicate.
Loves is a predicate. And furthermore, fool PT,
Predicate.
predicate. You can fool person P at time T is either true or false, right?
Verbs and predicates. So
Well, success or false. No, not necessarily, because runs. You know, if somebody runs, run is a verb, but it's not true or false.
Whether they're running or not running.
Well, running, okay, is running would be a predicate.
How's,
Or they run or not run.
how's,
Well, I mean, I suppose maybe you could make, I guess you could make every verb, you could turn every verb into a predicate by saying if that is happening or not. I mean,
is it true
thinking,
that this person runs?
If they,
or yeah. Runs. You could say you could say runs P. Well, you could say what you could say runs PT. This person's running at this time. Then that would be a predicate.
it was just more of a like word problem.
Yeah. Okay. So now, what about questions about we set this up for you now and did some examples. Any more questions about the homework? I think the reason there's not very many questions now is because not very many people have tried it, because I think when you try it, you're going to have lots of questions.
There's many people here either.
Well, that too. We're a little sparse today.
Well, let's start it right now.
Are we good? Okay, so if there's no more questions, we shall continue on. Now, before we get into we're going to finish up chapter 9 now. And we're going to actually skip chapter 10 and go on to chapter 11. But before there's just a few more things that I want to show you about chapter 9. Here are some examples of mathematical quantification. And we're going to be doing more stuff like this in the future. So this is kind of like a little bit of previews of coming attractions. So let's take a look at this concept of one-to-one. Now, you guys know how functions work? So like if this is the x-axis and this is the y-axis.
There's only one y for every x.
Yeah, like if you have something like this, is this a function?
No.
No, it's not a function, because you have this rule that says if you have one x and you have two possible y's for that x, then that's not a function, right?
Yep.
Okay. But now this is but what we have up here assumes that f is a function, okay? And it's the definition for f is one-to-one. And the way it works is like this. It says f is one-to-one. This is the definition of what it means one-to-one. For all x and y, range x is not equal to y, body f dot x is not equal to f dot y. Now, can you tell what that means?
Why can't x ever equal y?
No, it says in the range where x is not equal to y. It's for all x's and y's that are different.
Right.
All right, so let me give you an example. Here, let me give you an example. Now, is this a function?
Yes.
It is a function because, all right. But is it one-to-one?
No.
Now, why isn't it one-to-one? Because what? Here is a, oh, you know what? I shouldn't have this be y. Okay. I should have this be f.
F dot f.
Well, yeah.
Okay.
Are you with me? See, yeah, because see, the x and the y both are, the x and y are both on this axis. All right. Okay. So what is this saying? This is saying for all x, y, x not equal to y. Well, here's an x. Are you with me? And do you see that this is f dot x? But the problem is, here's a y that's different from x. Are you with me?
Yeah.
And what this is saying is that it says for all x, x not equal to y, f dot x is not equal to f dot y. But the problem is, in this particular example, f dot x equals f dot y. So this one is not one-to-one.
But it's still a function.
It's still a function, but it's just not one-to-one. But do you see how the point that we want to make here is how you can describe whether f is one-to-one using universal quantification? Are you with me? Now, what do we know about, what's another way to write this? What do we know about universal quantification? You know, what sort of rules do we have to manipulate?
So what not there exists? An x and y when they're the same.
What do we know about some tradings? What do we know about, how does universal double trading work?
You can flip the f dot x and the
But you have to put
But if you flip them, what do you have to do?
put knots in front of them.
Ah! If you flip them, you have to negate them, right? So look at this. Here's another equivalent definition. It says f is one-to-one if for all x and y in the range where f dot x equals f dot y, x has to equal y.
So they have to be the same.
Yeah, yeah. So see, here's one that is one-to-one. So this one's not one-to-one. Not one-to-one. And this one is one-to-one. Because what this is saying is that if you, for all, you know, here, f dot x equals f dot y, for all of these, the only way that can happen is if x and y are the same. You see you see how that's the same as that? And so you can define it either way, because we know by universal double trading that those are equivalent. So this is an example of how you use quantification to define properties of mathematical functions. Here's another definition. Okay, so this definition, it says, this is the definition of the inverse. Okay, so function g is the inverse of function f if g maps f dot x back into x. And I think we've actually, we reviewed what the inverse function was when we proved that one theorem, right? And so here's the mathematical definition. G is the inverse of f if for what? If for all x, x equals g of f of x. And remember, it also works the other way around. It's x, f of g of x, you know. Okay? So, and that's true. And what we're saying is that it's true for all x. All right? And now here's a third one. A two-argument function is symmetric if interchanging the arguments of a function application does not change its value. Now, so what's an example of a symmetric one, of a symmetric function? Suppose we have... I tried to draw that symmetric, right? So if what? If this is x, if interchanging the arguments. Oh, I can't draw this. Yeah, this was a bad example because this function is a function of if interchanging the arguments.
So you need something that takes...
That takes two, yeah. Yeah, and this is a function of one variable. Yeah. Well, I kind of botched that. I kind of botched my example here. Okay, because I need a function of two variables. Yeah. So anyway, f is symmetric if for all x and y, f of x comma y equals f of y comma x. Now, can you give me an example of a function that's, so rather than use this, I should use, what function should I use that's an example of symmetric?
F of x y equals x times y.
Oh, yeah, that's a good one. I was going to use equals, but f of x y equals x times y. And why is that? That's because because for all x, f of x comma y, so we know that f of y comma x then would be y times x. But what do we know about these two? They're equals. So we know that f of x comma y equals f of y comma x. So that's an example of a symmetric function. Well, it's a function of two variables, so it's a surface. Right? You have x and you have y, and then you. So it's a surface.
0 on the x.
All right. So anyway, that's the story of quantification. Now we are all now experts in predicate calculus, right?
Yeah.
So now what we're going to do is we're going to skip chapter 10 and jump straight to chapter 11. And now, let me give you a description of what's happening now. This is a big shift. because this course is really divided into two basic parts. Actually, the title of this course is Formal Methods. And technically speaking, we are now finished with formal methods. And the second, the Math 221, the title of Math 221 is Discrete Structures. We are actually ending formal methods now and starting discrete structures. We're starting it early, right? Okay, now, but here's the thing, and here's the whole idea. Now that we understand how propositional calculus and predicate calculus works, this is the logic that is the basis of all of computer science. And even it's the basis of all of mathematics, because after all, computer science is just applied mathematics, right? It is at its heart a mathematical discipline. Computer science is. Okay? And in fact, it's a logic discipline as well. Okay? So now what we're going to do from now on for the rest of the course is we are going to take propositional calculus and predicate calculus, and we are going to apply it to several different theories, several different disciplines. You see what I mean? So now what we're going to do is we're going to take what we know about propositional and predicate calculus, and we're going to use it as a tool to investigate these other areas. And one of the areas that we're going to investigate, the next area that we're going to investigate is sets. All right? In the future, we're going to apply it to programming. We're going to apply it to functions. We're going to apply it to graphs. You see what I mean? So the whole idea is that we have the propositional and the predicate calculus. Now starts how do you apply it to other disciplines. So this is a big sea change in what we're doing from now on. Because you've got all the tools now. You know just about everything there is to know about propositional and predicate calculus. There's some theory, there's some higher level theory stuff that's actually in chapter 10. If you're interested, you can take a look at that. But it's not necessary to know that stuff to know how to apply propositional and predicate calculus to these other areas. And so the big area now that we're going to apply our theory to is to sets. That's the first one. A theory of sets. All right? So, here we go. Sets. All right? And notice the order that we're doing these things in. In some math treatments of mathematics, they start with sets. Okay, the sets are the starting point for math. But for us, it's not that like that. Our starting point is propositional and predicate logic. And sets are defined in terms of logic, not the other way around. Are you with me? Okay, so this is we just want to note that. Now, you guys have done sets before, I think, right? Have you guys done, little brace with the sets? Have you done Venn diagrams?
Oh, yeah.
Do you remember you know how Venn diagrams work? Have you ever heard of those? Okay, so this is, you already know and you've already been introduced to this, but now we're going to tackle it from first principles based on logic. Now, the main thing about sets that the first thing about sets that we want to note is that sets can be described in two ways. Sets can be described in two ways. All right? And these two ways are called set enumeration. One is set enumeration. All right? And let me give you an example of what set enumeration means. What does it mean to enumerate something anyway?
List it up.
Yeah, just to list it out. Enumerate. Just say what they are. Just say what elements are in that set. So here, and this is the way that I think that you're used to seeing sets, a particular set defined. So here's an example. Suppose we have this set. And the way you denote a set is you use these curly braces, right? So curly brace for a set, okay? And how about this? 0, 2, 4, 6, 8. So what you do is each one of these elements in the set, you enumerate it and you separate them with commas. Are you with me? So that's how you do set enumerate. That's how you enumerate. A set is a collection of elements. Informally, it's a collection of elements. And the way you enumerate that is you just put that collection in. And so, you know, remember, this is what a type is too. A type is basically a set. It's a collection of elements, right? So here's an example of how you would enumerate a set. But now there's another way. There's another way to describe the elements of set, and this is called set comprehension. Okay? Set comprehension. I don't know.
Let me guess, use quantification?
Oh yeah. Well, yeah, sort of. Yeah, we sort of use quantification. Now, so I can't think that the English word comprehension, to comprehend something is to understand. I don't think that has anything to do with.
Comprehensive is.
Yeah. Okay. So let me give you an example of how you would denote the elements of a set using set comprehension. What you do is, again, you use a curly brace. Okay. So whether you do it with enumeration or comprehension, you use the curly brace. But now, instead of just listing the elements that are in this set, basically what you do is you do this is like. This is very much like. In fact, it's not just coincidentally that it's like. It is very much like a quantification. But it's not a quantification, it's a set comprehension. So we have the curly brace, but in the same way that we have 3 compartments for a quantification, we have 3 compartments for a set comprehension. Are you with me? And what are those 3 parts when we do a quantification? What are those 3 parts? We have the what? The dummy, the range, and the body. Similarly, the set comprehension has the dummy, a range, and a body. Are you with me? So in that respect, it's very similar, but it starts with this brace. So here's an example. So here's the dummy. In this example, dummy X. We'll annotate it. We can optionally annotate it. Okay, so this is X type, what? What is Z? Integer, right? Range, and for this range, let's say 0 less than or equal to X less than 5. 0 less than or equal to X less than 5. And now what does what does the type of the range have to be in a quantification? The range in a quantification always has to be type what?
Boolean.
Has to be, and similarly, Boolean. This is either true or false, right? Either X is greater than 0 and less than 5 or not. Yeah? Okay, Boolean. And then here we have the body. Okay, so here's the body. So let's say this is 2 times X for this example. And then we close the brace. Are you with me? And so this is an expression.
The exact same.
Ha ha ha.
Hey.
Did you notice that? What are all the possible values of X? The possible values of X here are 0, 1, 2, 3, and 4. But the elements are 2 times 0, 2 times 1, 2 times 3, and 2 times 4.
And 2 times 2.
Oh, sorry, did I skip 2? 2 times 1, 2 times 0, 2 times 1, 2 times 2, 2 times 3, and 2 times 4.
So enumeration is better for small sets, but comprehension becomes better when your sets
Get really, really big. Yeah. Okay. And here's the thing. 11.2. 11.2 shows. Now, what do we have on the left side of 11.2?
Enumeration.
We have an enumeration. And what do we have on the right side?
Comprehension.
A comprehension. So 11.2 shows the connection. Shows the connection between set enumeration and set comprehension. Between set enumeration and set comprehension. Are you with me? Okay? And so let's take a close look at it. What is it? You know, what is this? On the left, we have, now you understand, we have these subscripts. E sub 0, E sub 1, E sub 2, all the way up to E sub n minus 1. So this would be E sub 0, E sub 1, E sub 2, E sub 3, E sub 4. Yeah? Okay? And what it says is that that equals, we'll talk about types in a minute, but we have equals here. We don't have equivalents. Is a set a Boolean, yes or no? Is it type Boolean? Is a set type Boolean? It's not a type Boolean, it's type set. Are you with me? It's just a set. I mean, it's not, it doesn't say anything. It just, this is a set, this is this set of elements. Yeah. So notice that we don't have equivalents. We have equals. Are you with me? Because equivalents is only for Booleans, equals is for Booleans or anything. As long as the two things on both sides are the same type, right? Equals has to, you have to have the same type, right? All right, so what we have is E sub 0, E sub, and now what this is the same as, it's the same as the set of all x. Oh, and by the way, this is how we say this. The set of all x, range 0 less than or equal to x less than 5, body 2 times x. Right? So we say, we identify these compartments the same way we identify them with quantification, right? And so it says that that enumeration, E0, E1, E2, dot, 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 all the way up to E sub n minus 1, is equal to the set of all x range. Now look what we have. Everywhere there's an element in the enumeration, we have x equals that element. And then we have or, right? Disjunction. Or x equals the second element, or x equals the third element, or x equals dot, 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 all the way up to x equals the last element. Body what? X. Yeah? So let's do some examples. So what is the set AB? What is the set AB? Using this. This is the enumeration, right? This is set enumeration. We enumerate it's AB. So what does that equal? That it's equal to the set of all what?
X.
Set of all x. Range what?
A is less than or equal to x.
No, not a less than or equal to x. No, 0, no.
N minus 1.
No, not less than or equal to. Where are you getting these less than or equal to? I don't see any less than or equal to up in there.
Range true. Range true.
I don't see a range. It doesn't say range true up there.
X equals.
What are you talking about?
X range X.
X equals.
X equals A or
B.
X equals B.
X equals B. Are you with me? You can't say, look, you can't say X equals, wait, sorry. You can't say X equals A or B like this because A and B aren't Booleans, they're numbers. You can't or two numbers. Okay, so X equals A or what?
X equals B.
X equals B, body what?
X.
Body X. Now, does everybody see how that works? Are you with me? And what is C here? What's the set? You know, any number. What's the set C, D, E? What's that set?
X.
That's a set of all X.
Range X equals C.
X equals C.
Or X equals D.
X equals D.
Or X
Or X
equals E. Body
equals E. Body X. All right? Are we good? So let's take a look at this comprehension. So in general, we have X, and we'll annotate it with type T, okay? Range R, body E, where E is some expression, all right? And right here, we have this optional type. So here, this is an optional type. In the dummy, Okay, so that's that's the dummy part. And this is the range, and it's type Boolean, right? And this E is the body. All right? And now here's something else that we have to be aware of. This E does not have to have the same type as X. Okay? They can be different types. So E need not have the same type as X. Okay? Now, I'm going to give you an example that we're going to use here for the next few minutes to illustrate this. And here's the set that we're going to describe. The set is going to be the set over X type integer, range x equals 5 or x equals 10. X equals 5 or x equals 10. Now here's what this 5 and 10 is going to represent. This 5 is going to be, if you go to the sporting goods store and you buy 5 Frisbees, this is how many Frisbees you're going to buy. And this is going to be, you're going to buy 5 Frisbees here, you're going to buy 10 Frisbees here. So what this is going to be is, so the body is going to be Frisbee price X. All right? And this is to illustrate the fact that Frisbee price is not type X, because X is an integer. X here is either 5 or 10. But here, the Frisbee price, this is how much you'd pay for 5. So this is the set of prices that you would pay for either 5 or 10 Frisbees. And usually, so let me just give you an example. This is going to equal, just to show you that it's going to be in dollars, I'll just make up a price. Let's just say 25, if you buy 5 Frisbees, it's going to cost you $25. But if you buy 10 Frisbees, they give you a little bit of a discount. So instead of being $50, let's just say it's $45, right? So here's $45. All right? So this is a set of dollars, right? But X is not type dollars. X is an integer. So you see, this body need not have the same type as X. Are you with me? Well, wait a minute. Now, what do you think the type of this whole thing is? Now, here's something that's a little strange. Remember when we had a quantification, like if we had, yeah.
Type set.
Yeah, well, I mean, if we had a quantification here, do you remember how did this work? If we had star X, range R, body Q, do you remember what the type of the whole thing was? It's the type of Q, right? So type of quantification is the type of Q. Type of quantification.
This type of body.
Yeah. Is type of the body. But that's not the case here. The type of this is not the type of the body. All right? And the point is that this type right here is not dollars. Yeah, the thing is, one of the elements of the set is $1, but the set itself is not $1. The set itself is a set of dollars. Okay? So our point here is that if E has type T1, let's draw this over here. This is another thing that mathematicians don't take a great deal of care. In computing, all the elements of the set have to have the same type. Okay, so in computer science, in the computer science treatment of sets. Okay, so but anyway, because type theory is crucial. So, what do I want to write down here? So, if E has type T1, if E has type T1, then the set has type, now here's how we denote it. We say set parentheses T1. That's how we write it. Okay? So set T1 is the type of the whole, okay, so tell me, what is the type of, here, let's do an example. The type of 1, 2, 3 is what? What is the type of this?
Set.
It's set, set, parentheses, are you with me? It's set, parentheses, no.
Okay, then just
Integer.
Yes, it's set integer. Now, is everybody clear on this?
I think it's a set of natural numbers.
Well, it could be a set. Yeah, if these, yeah, it depends on what the type of these are. Yeah, or could be, yeah, okay, all right, good point. Could be set n.
Or maybe it's only positive integers.
Or it could be. All right. Could be
You don't want to keep doing this.
set. I think you'll run out.
Whole numbers.
Set z plus.
Real numbers.
Well, no, real. Oh, okay, because there's no decimal, but there could be. Oh, well, okay. Anyway, you get the point. All right. So here, let's do some practice. Let's do some practice going from. Let's do some practice going from comprehension to enumeration. So here's some practice. Let's do this. Set I range 0 less than I less than 4 body I. Okay, so Ben, what do you think this set is if we were to enumerate them?
Let's see, is it just I on the left? Okay.
Yeah.
I would say that it is 1, 2, 3.
Yep. 1, 2, 3. Okay. Who's next? Set on I, 0 less than I less than 50, and even dot I, body I. Okay, what do you think?
Be 2, 4, 6, 8, 10, 12.
All the way up to 48. So 0. Wait, did you say 0? No, you said 2, right? Okay, so 2, 4, 6, dot, 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 up to 48. Yeah? Is everybody good? Okay, how about, okay, so Kyle, it's your turn. How about the sum, not the sum. How about the set over I? Oh, well, that's how we say it. We say the set over I. Okay, so that's how we'll speak it. The set over I, 0 less than 2 times I, less than 50, body 2 times I. Well, what are the possible values of I such that 2 times I is between 0 and 50?
That's the same thing as and even dot I, isn't it?
Well, 2 times I, yeah, what are the possible values of I such that 2 times I are between 0 and 50?
1 through 24.
1 through 24.
But 1 through 24 times 2 is the same as
But 1 through 24, each one of those times 2 is,
even numbers between 0 and
yeah, so this is 2, 4, 6, dot, 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 48. Is everybody clear? Yeah? Okay, how about this one? How about the set over x range, let's do this. How about the set over xy, because this could be, just like in quantification. Yeah. Okay, so set over xy, 1 less than or equal to x less than or equal to 2 less than or equal to y less than or equal to 3 body, oh Mason, you got the hard one, x to the y. Now what the heck does this mean? What's the conjunctive meaning? What is this conjunctive meaning? 1 is less than or equal to x, and x is less than or equal to 2, and less than or equal to y, and y is less than or equal to 3. So can you give me the list of all the x's and y's that do this?
So,
Are there? I don't think so. So the hard thing is to figure out what possible values of x are there.
well, x is 1.
X could be, if x is 1, then y could be what?
Y could be 2. Or 3.
If x is 1, couldn't y also? No, wait.
Y can be 2 or 3. X can be 1 or 2.
Right?
1 to the 2, 1 to the 3.
Come on, you're not Mason.
I am.
Oh, you only know that's not.
Yeah. We're going to do enumeration. Yeah, we're going to go from we're going to go from comprehension to enumeration.
So it's like 1 squared.
1 squared,
2 squared.
2 squared,
And then
1 to the third, 2 to the third. Good. Okay. I know it's time to go, but I want to just get to the end of this set of examples. Set over x, 0 less than or equal to x less than 3, body, x times y. Okay, now, the whole concept of bound and free applies.
Yep.
Okay? So what do you think, Ben?
It'll be 0 times y,
Yes.
1 times y, 2 times y.
2 times y. And just one more, Cale, for you. Set over x, range 0 less than or equal to x less than or equal to, 0 less than or equal to x less than 0, body, x times y. Ha-ha!
B doesn't exist.
Well, what you're saying is that this is false.
Yeah.
Whoops.
So then
Wait. What did I say? 0. Wait. 0 less than or equal to x. Less than 0. Body. Yeah. Sorry. Yeah. So what we're saying is, if this is false,
Yeah.
then there's a. But what? So how many things are in the set?
why?
0.
No, we don't say 0. No, we don't say 0. How many things are in the set?
False.
No, we don't say false. False is Boolean. This is set in. No.
You just close the bracket.
Yeah. There's just nothing. That's the empty set. All right. Okay, good deal. See you next time.